running out of the resource.
Right, so what we're going to do here is, I'm going to talk about the price going up and up and up as we start to run out. And we're going to talk about it more as the price goes up until we hit a backstop price, which would be the price of solar. In reality, what you do is you have the price go up and up and up on sort of oil that's in really easy to get places. And then you hit a price where now all of a sudden it's good to go out and get it from deep water drilling in the Gulf. So you make that switch from like on the land to the Gulf. And then the price starts going up from that. And then you get to the point where the price gets high enough on that, then that makes sense to go and get it from the frozen Arctic. So you switch over from the Gulf of Mexico to Arctic drilling, right? And what we've kind of done with shale was all of a sudden we took that and we kicked it all the way down to a very cheap thing again. So now the price has to rise back up from cheap shale before we get to the Arctic thing again, which is probably why BP just said forget the Arctic drilling. They had the rights to do it going back a ways, and they started to go in and figure out the mechanisms. It was going to be super expensive, and like 2 years ago they just canceled it.
So the reason that the potential reserves increase is because we now are capable of using other, like, more expensive technology to...
Yeah. So like the scientists are working at BP now to figure out how do we get oil out of frozen underwater places in the Arctic, and there's a lot of problems with that, but they're going to work it out because eventually they know the price is going to get high enough where that's going to be in the market. Like, that'll be useful. Okay. All right. So the pieces of the math here are the following. What I've got up here, this B, measure of B, is basically the trapezoid. This would be a lot better if I had a picture to show you too, I think. This is the area under the demand curve, okay, between the vertical axis and some level of consumption Q, okay? But without the cost part, without the part below the cost line taken out. So this is sort of the consumer surplus, but without the part where you actually have to pay for it. Yeah?
Sorry, is X just like another representation of quantity?
Well, X, usually when you do integrals, right, you have your variable that you're integrating over,
right,
and then you've got like 0 to Q is my limits of integration.
Right.
So I'm integrating over 0 all the way out to some quantity of consumption,
right,
Q.
So the X is quantity.
Well, X is just the variable in the integral that when I go and do the integration and then I put the limits in, I get a function of Q out.
Okay.
Okay? Does that make sense?
Yeah.
Yeah? Okay. So basically what this thing here is the area under the demand curve between 0 and some level of consumption Q. Okay? Normally when we talk about consumer surplus, we take out the part under the supply curve. Right? It's between the demand curve and the supply curve. This is just under the demand curve without the supply curve part taken out. But what I'm going to do down here is I'm going to take it out separately. So that's why I've got the minus CQ. This part down here is the benefit from consuming minus the cost. Okay? Now what we're going to do is we're going to throw in, oh, and also this is just the demand curve formula. So I've got an intercept and a slope, and that's going to show up in the spreadsheet we're going to look at in a few minutes. The total quantity that we're going to talk about is going to add up to some big Q bar. So QT is the amount you consume in any period. Q bar is the aggregate of that. And in the end, when we use it all up, these things have to be equal. So we've got a constraint, our benefit, our cost, and we're going to put all of that into a Lagrangian. So we do have to use a Lagrange expression today. Okay, we've waited it as long as we could. But with multiple periods, there's really no other way to do this. So the messy pieces of this are first the thing that we're maximizing, which is the present discounted value of the consumer surplus. Benefit part minus the cost part, present discounted value of that. And we're going to add all of those things up from now until infinity. Okay, the problem is going to be that eventually we're going to get to where Q is going to have to be 0. And when we want to run out, because we have a substitute we're going to switch over to, we want Q to be 0. So we can do this out to infinity, but at some point there's no more consumption. Okay? And then we've got the constraint part, which is that over all time, the sum of all consumption should add up to Q bar. Yeah?
How do you make assumptions about, like, because costs are always changing, right? Or like not all, or they change over the long periods of time. So how do you make?
Yeah.
So how do you like assume how to like?
I've made it just C, right? The cost of getting it out of the ground. Because I don't want to make the math really, really messy.
Okay. Okay.
So in grad school at Stanford, I was in the econ department, but because I liked environmental stuff, I went over and took a class on sort of petroleum engineering because they have a big school with that there. And there I had to learn how to do these problems with like 20 different grades of oil or coal or whatever you're pulling out of the ground. And they give us these problem sets. And this problem here, which we're going to see is solvable pretty, was like 3 days of programming in that model. So it's doable, but unless you're going to be a petroleum engineer, I think we can probably like make the simplification. Yeah. Okay. So here's the Lagrangian, and then we've got two first order conditions. So this is really the only time when I'm going to like, you have to kind of remember multivariate calculus. Okay. But the idea, if you don't, is basically thing you're maximizing, the constraint that's tacked onto it, and in general what you do is, right, you write the constraint so that if it's violated, this is negative. So this is kind of the price of violating the constraint, and when the constraint's violated, it pushes down the thing you're trying to maximize. Right? So in the end, what you do is you find the values of the price of the constraint, lambda, shadow price, shadow value here of the constraint, and then the values of Q in every period that maximize this thing. So that gives us two sets of first order conditions. One is the derivative of this thing with respect to Q in any period. So there's T of these, it's not just one constraint. Notice it's subscripted by T. And then we've got the constraint with, the first order condition with respect to the Lagrange multiplier, which just kicks back the constraint. That's usually what it does, okay? So we're gonna work a lot with those first order conditions. Now, the thing is that they're basically going to describe what we saw last time in terms of the dynamically optimal allocation of water, I think we talked about, across 2 periods. That was the exact same problem in a very simple 2-period setup, right? Basically what this is doing is saying allocate it so on the margin the contribution to consumer surplus is equal in present discounted value across the 2 periods. That's what this is telling you, okay? But this is what you can do when you want to do it with more than two periods. Now the nice thing, this is why economists sit back and relax when we talk about things being scarce, right, is because if we have a firm that takes prices as given, so when they take prices as given, we're going to stick P in here. So P times Q is revenues, minus C times Q is costs, that's firm's profit, okay? They're going to take prices as given, so they're not going to treat P as a function of Q. They're just going to treat it like a price that's handed to them. Later at the end of class, we're going to talk about a monopolist who does treat price as something they can influence, like OPEC, right? But for now, they're going to treat it as like it's a price handed to them. And when you do this math here, you get this first order condition. So now I'm just taking the derivative with respect to Q again. So P minus C. But then I can take P minus C, I can substitute back in for what price is. Right? On the last page I said, 2 pages ago, the demand curve tells us price is equal to an intercept A minus slope B times Q. So I take that and I substitute it back in for price, and I get a first order condition or a set of first order conditions right there that, if you take a mental quick picture of that, is exactly the same as the first order condition that the social planner would pick. Okay? So competitive resource extracting firms, as long as they own the resource, so they know if they leave it there until tomorrow, they can consume it then they'll do this dynamic optimization problem, and they're going to produce first order conditions that are exactly the same as what the social planner would do. So we're going to get dynamic efficiency by letting firms just profit maximize. Okay, so that's like one of the first things you learn in a natural resource class, right? Letting the market handle these things is good. Now the problem would be that if the firm doesn't own the resource, if they're fighting over it, I'm going to drink your milkshake thing, then they're not going to play this dynamic optimization problem. They're going to do a static thing because the dynamic part means nothing to them. Next period, the stuff's going to be gone, right? And the static solution here is going to take quite a bit more out today than the dynamic solution would Jess? Okay, so it is important to just remember that we've just sort of proven that competitive markets are going to do this in an efficient way. They're going to do the socially optimal dynamic maximization of the total amount of consumer surplus thing, but they're not necessarily going to be sustainable. Sustainable, again, requires consumption being fixed over time, per capita consumption being fixed over time. And here we're definitely going to have the amount of oil that's getting used every period going down over time as you get closer and closer to running out. The question is, for sustainability, can you replace the oil with something else? Right, so what would Hartwig say you should do with all of Exxon's revenues? In practical terms, what would be a good solution? So you should be taxing the hell out of Exxon and taking the revenue and using it to do what? What's a good renewable technology that can substitute on the margin for oil? Right, so you should be coming up with really good solar panels with all the profits that all the oil companies are earning. That would be what Hartwig would say, right? And it's hard to actually get us to put huge taxes on oil companies to get that revenue back out. So we're not really doing that, but that would be okay. All right, so I said hoteling was going to come back again, and this is hoteling. This is what hoteling is really known for. Hoteling before was just kind of the travel cost thing is like an oddity, but hoteling's rule is kind of like, you know, his main claim to fame. And what's useful about hoteling's rule is it's going to basically give us the way to think about how prices for natural resources move over time without having to solve out that thing, okay? Which makes it really useful for exam questions, for instance, okay? Because you can solve problems using hoteling's rule with a calculator and a pencil, not with a spreadsheet, okay? And we do have now 2 hoteling problems, I think, on the problem set, right? Numbers 4 and 5. Yep. So 2 versions of questions that use exactly this. And I don't think we say necessarily use hoteling's rule in the question, right? So you now know what to look for. So the idea behind hoteling's rule is take that first order condition that we saw a few minutes ago. Remember that right there? And I'm going to rewrite it. I'm going to cross multiply so it's not fractions anymore. So I'm just going to take the so it's set equal to 0. I'm going to bring part of it to the left. I'm sorry, to the right. I'm going to multiply up to 1 over r, 1 plus r to the t minus 1, and I've got this expression. Okay, so that's the same expression we saw a few minutes ago. It's just been manipulated a little bit. Now what I'm going to do is I'm going to solve out. Well, I'm going to put p back in. Okay, I'm going to replace what the firm is going to think of as a minus bq with what the market tells me that should be, which is just the price. And what I'm going to do now is ask, how does the price move over time? Okay, what hoteling's rule is all about is there's a condition that we can impose on the way price of a natural resource is going to move over time. And in particular, it's going to move over time at the rate of return on whatever the alternative investment would be. Okay? So the story I told you a few seconds ago is basically hoteling's rule, where I'm an owner of a barrel of oil underground. I know that if I leave it in the ground today, its price might be $1. I can leave it there, and tomorrow it's going to be $1.10. So if I take it out of if I leave it and take it out of the ground tomorrow, what was my return on the investment of leaving it in the ground? 10%. Whereas if I have it in the ground and I take it out today, I'm going to get $1. I can put the $1 in the bank, and the bank might be paying me 4%. So next year I come back, and what's my return? Well, I got $1.04. Whereas if I left it there, I get $1.10. So the rational owner of the barrel of oil in the ground, according to hoteling, would take the oil out of the ground today. No, I'm sorry, would leave the oil in the ground today. I got it backwards, right? And that's going to be the force that's going to lead us to a condition here that's going to basically make the dynamically optimal thing hold over time, okay? So hoteling's rule is basically what we call a no arbitrage condition. So the idea is that arbitrage, the ability to sort of pull profits out of the world by noticing like places where you can buy something for less and sell it for more. getting rid of all of those opportunities is going to leave us in a situation where prices have to rise at the rate of interest. Okay? Now we could get the prices rising as the rate of at the rate of interest from all the math I just showed you from that Lagrange expression. We solved for that. But we can also get it out of this nice intuitive story. So here's an example of it. Take the two equations that I just showed you, okay, and take the ratio of the price in the next period, PT plus 1, to the price in today's period, PT, okay? The other side of that equation was lambda times 1 plus r raised to the t minus 1 and lambda times 1 plus r raised to the t, okay? So that was just that expression there. And what Hotelling is going to do to make the math even less messy is just say it's free to take the stuff out of the ground. You can do Hotelling's rule with the cost, but it's not as pretty when we solve it out. So that you poke a hole in the ground for free and the stuff just comes shooting out. That's Hotelling's view of the world. Okay, so if we do that, then the ratio of the price tomorrow to the price today is just going to be the lambdas cancel out and the t's cancel out, and we just have 1 plus r. Okay, so you can kind of see it here. This is the return to leaving the oil in the ground for one period. Price tomorrow divided by the price today. Right, if that was $1 and that was $1.10, that would be 10%. This is the return to taking it out and putting it in the bank. All right. So if the return to leaving it in the ground today is bigger than the return to taking it out today and selling it, then what's that going to mean we're going to do? We're going to leave the oil in the ground more today. More owners of oil are not going to extract it. What's that going to do to the price today? When fewer people extract it today, there's less supply today, so the price today is going to go up. As the price today goes up, what's that going to do to this ratio? It's going to go down, right? That's going to make this inequality become an equality, right? This is what a no arbitrage condition means. It means people doing the profit maximizing thing is going to make the opportunity for that thing disappear. It's going to make the opportunity for making the profit off of holding on to the oil for another period go away as more people do it. The flip to that would be, let's say the inequality went the other way, where the value of taking it out today and selling it is a lot bigger than the value of leaving it in the ground. That means more people are going to take it out today to capitalize on the higher interest rate. And when that happens, the supply today is going to go up and the price today is going to go down. When the price today goes down, the price tomorrow divided by the price today goes up. Okay? So that inequality there, which the less than, is going to become an equal sign. Right? So if this thing's ever out of equality, then the market supply price forces are going to push it back into equality. That's the idea. Okay? So in the end, we're always going to end up with this ratio here holding. And that ratio is basically, if you go back and kind of think about it, it's the same thing as that ratio, which is really the same thing that's embedded in the first order conditions from the big messy Lagrangian. Okay? So we've got optimality in terms of the dynamics of oil extraction just from sort of this intuition about two ratios having to be equal. Okay? So when I give you a problem then on the test, for instance, that asks for what is the price going to be in so many years if the interest rate is this and the price today is this, Hotelling is going to tell you exactly what the price in that many years will be, right? We just basically solved it out by taking the math. So the one thing I did here to help you out, going from there to there, was I took a difference equation, which has PT and PT plus 1 in it, and I did the annoying math to solve it out for PT as a function of t, and the first period, P1. Okay? There's mathematical solutions for solving these things iteratively that get you from there to there that you don't have to know. Okay? As long as you understand where that came from, then you can just memorize that if you want to. Okay? All right. So that's on the problem set already. So you'll see a couple of examples. What we want to do now for the next 10 or 15 minutes or so is go to a harder problem than Hotelling, but basically it's going to give us a spreadsheet version of the problem that's going to let us answer lots of questions about backstops, right, and running out, and when we're going to run out, and if you're a policymaker, what would you do in terms of subsidizing different kinds of backstops and things like that. Okay? So I'm going back to the same equation again. This is the equation that popped out of the Lagrangian. We're going to use it over again. But now what we're going to do is solve out for the Q. Okay? So what I want to know now is, along the optimal path, which we know is the same path that competitive firms would take, we solved for that a little while ago too, how much output would get produced at any given period? Well, it's going to be this, which has the demand parameters in it. It has the cost of extraction in it, which we're holding constant. And it's got the Lagrange multiplier in it, which is kind of an annoying thing, right? Because you kind of know what the demand curve looks like. Right? You can estimate that. You know what the cost of getting oil out of the ground is. That makes sense. You know what the interest rate is. You know what the time period is. But what's this lambda thing? Right? That's weird. So that's the part that we're going to use the spreadsheet to solve out for what lambda is. Okay? That's the part we don't really know. The other things that are going to work into the problem are that you can never consume negative amounts of oil. So that when you get to 0, you're kind of done. The total amount is going to add up to Q bar, and I'm just going to cap my thing out at 20 periods, but we're going to run out of it long before 20 periods in all of the examples. The demand curve, same as before, and time is an index. Yes?
So with the whole shadow pricing thing and the constraints that you had with the lambda and the bracket Q bar minus summation of QT,
Yes.
how does that ever get violated? If that's like you mathematically Q bar is a summation of QT, how can you ever violate it?
Well, because you can have the price path be such that you're going to run out before, right? It wouldn't be the solution to the problem. Basically, what we're going to do right now is we're going to solve that dynamic problem. Essentially, we're going to solve for the lambda that makes that dynamic problem hold, that solves it optimally. Okay? What we're going to see is there's lots of values of lambda that make it not solved, where you either run out too soon while people still want to consume oil.
Yeah.
They get positive consumer surplus for it, but you don't have any left.
Yeah.
Or you get to the point where nobody wants it anymore, but there's still some there.
Okay.
Both of those are not solutions to the social planner's problem.
Okay.
Okay? And that's exactly why we want the spreadsheets. The spreadsheet's going to tell us what lambda has to be to make the answer to that right. Okay? Okay. So, yeah, here's the equations again. Remember that when demand falls to 0, which is basically when the price hits the choke price. So the demand curve intersects the vertical axis at A, and then drops down. When the price gets up to A, nobody wants any anymore. Okay? That's if you swing this over and bring that over and bring price over there, when A equals the price, Q is going to be 0. Okay? So in our simple world here, when we have a demand curve that intersects the vertical axis, what that says is when the price gets up to A, people have other things to buy with their money. Okay, that's the simplest form of a backstop technology. It's just when they don't want the oil anymore. When it hits if you get $6 a gallon, we say you're done with oil. That just means, it doesn't mean people aren't driving anymore. It probably means that at $6 they can be in solar cars. Okay, that's probably more like $12. Okay, so let me skip over, because this is the spreadsheet, but let's go to the actual one that I generated that from, so that we can see how it works. Okay, so this is the spreadsheet that's on the Sakai site, okay? And the bonus question on the problem set, worth 8 points, basically just requires you to use my spreadsheet. So it's like the easiest 8 points you could possibly get. Everybody should get. You might not get the rest of the problem set right, but you should all have an extra 8 points, no matter what. Okay? So the way it works, so you can kind of see the pieces of it, are what I've calculated here is, okay, so periods 1 through 20, that's easy. Quantity is just the expression that I just had up there for Q a few minutes ago. Okay, that's what this is up here. It's kind of hard to see if you don't have it in front of you, but that's the expression for Q. And what it does is it pulls pieces from up here. This is sort of my parameter list. Lambda is a parameter I've got sit here at 2.7983. You're going to ask, like, why 2.7983? What we're going to see is 2.7983 is the value of the shadow price that's actually going to lead you to run out exactly when you want to run out. That's the solution to the problem, okay? R, I just give you an interest rate of 10%. A, the intercept is 8. B, the slope It's the minus is actually built in. So that's like downward sloping with a slope of 0.4, and the cost is 2. Okay, so those are just, you can change any of those parameters around. It won't break the spreadsheet if you want to mess with that. So, and then you've got the quantity truncated, which is just the quantity, but if it ever wants to be negative, then basically the constraint says it's just 0, because you can't consume negative oil. Okay? Then you've got the price, right? And that's just the demand curve. You know, price given the quantity and the A and the B. Okay? And then cumulative extraction starts off with the quantity that you consume in the first period, and then it's the quantity, it's the extraction from the previous period plus what you consume that period. So then here it's that plus what you had before, and there it's that plus what you had before, and works its way down. Okay? So now what we're going to do to actually solve the problem, and over here I've got a graph set up to show you over time what's happening with the quantity that's being consumed, and like in all dynamic problems, it falls until we run out. The price is going to rise, that's the price there, and it's rising according to Hotelling at the rate of interest. So when things rise with exponential rates of interest, they tend to go up like that, curve up, okay? And then this is the cumulative extraction. And when we make it so that we run out, we get to 40, which is the total amount of oil in the ground. So I wrote 2.7983 over there so I wouldn't forget, because it took me a long time to get to that number, messing around with these numbers. But let's just try a different value of lambda and see what happens. So if I make lambda lower, I lower the constraint, go to 2. Now all of a sudden, the price of oil at the beginning dropped, right? There's a lot more consumption. And what I end up with in the end, right, is the price working its way up to 8, but not until we get all the way out here to the 21st period, okay? And by that time, the total extraction has gotten up to 73 before we get to a price where nobody wants it and they stop consuming. This isn't feasible because we said there's only 40 units in the ground, okay? So in reality, what we had was some point back here where people still want oil, but we've run out somewhere in here. We hit 40, okay? But people still are demanding it. So that can't be a solution to the dynamic programming problem, okay? So basically what lambda is it tells you kind of where the price path begins. And here I set it too low, so the price starts off too low, so we end up consuming too much, and we run out before we want to. Let's make it bigger. So if I make it 4 instead, now we start off with a really big price at the beginning, okay, 6. And by the time we hit 8, where nobody wants it anymore, we've only used up 13 of the 40 gallons in the ground, okay? So what we end up now with is something where you know, there's valuable resource left that nobody wants, and that's a loss of value, okay? So that can't be the solution either. So what you're going to basically do to solve these things is just iterate. So you find that's too big and 2 was too small, so then you could try 3, and that's going to be too big. You still have stuff left in the ground, and you know, we already tried 2, and that one was too small because people want too much, so we go up to 2.5, right? And we're getting closer now. The over extraction isn't so high, and you keep going back and forth until you get to 2.7983. So yeah, it doesn't take that long to get out to several digits once you kind of figure out where to cut the 2 ends and take the midpoint over and over again. So now we're running out exactly pretty much at the point where nobody wants it anymore. Now this is always a little bit messy because we're talking about discrete periods of time, and we run out here sometime between period 8 and 9, right? And we kind of hit the we hit the intercept on the demand curve sometime, I guess, around 9 to 10. So it's really about period 9 there where I'd say we kind of run out at the same, yeah.
I just got a news alert about Keystone XL.
Yeah?
Yeah, that it just got Nebraska's approval during the regulatory hurdle.
Yeah. Are you on alerts for like,
Yeah.
wow,
Yeah.
that's some
So I
dedication
thought
there.
that possibly-
But that's good to know. So I will say on the Keystone thing, because I used to do a whole class on Keystone, that I think the Keystone's probably actually the right way to go, because there's so much oil there that's coming out anyway, and what they do with it now is they put it on rail cars. And oil coming out of North Dakota and tar sand oil coming out of Canada has, there's a term for it, and an engineer will know the term, but it lets off a lot of vapor, and the vapor accumulates inside the rail car, and if you like bump into these things, they explode really easily. So they're taking this stuff out kind of regardless, but they're taking it out right now in a way that's really A, expensive, B, rail cars are actually bad for the environment too, because most of them are diesel powered. And then they tend to explode a lot, and like there was an entire town in Canada around Montreal that was actually like vaporized by an explosion from a whole train that was carrying oil from tar sand. It like killed, it's a small town, so it's like 60 or 80 people, but nothing was left, like it vaporized it. Rail's just not a good way to take oil out. So I would have rather, in Canada in particular, that they just never took it out, but they got to a point in investment there that they were going to do tar sand regardless, and now how are they going to get rid of it? Probably better to do it with the pipeline. Although I think the pipeline leaked in North Dakota last week too. There's another story there where they had a leak in it. They said they contained it relatively quickly. But tar sand oil is really gummy and gooey. You guys know how to get tar sand oil out? You have to first make steam by burning coal, really, to make steam, and then you force the steam down underground, and you steam the tar sand, and that makes it liquefied, and then you can suck out it using a pump and get the tar sand oil out. So you actually have to burn coal to get tar sand oil out of the ground. When they talk about it being a high carbon fuel, it's both because burning it is bad and extracting it is bad. It's just cheap once you kind of build those things. So yeah, you can say a lot about the whole pipeline thing. It's really interesting. Okay, so the rest of the panels down here, if you want to play around with these, if you try the problem set at all, you'll see some of these things. Basically, mess around with the different parameters up here. Okay, so here's one where what we do is increase the demand intercept. So from 8 to 10, the demand curve shifted up, which means now what we have to do is get to a higher price before nobody wants it anymore. So that's going to lead to a much higher starting price, okay? But then the price is actually going to rise more quickly when it starts at a high price. We're going to work our way up, and we're going to run out now at period 7 instead of period 9, okay, as a result of the new demand. But that required a new starting price and a new lambda, or else we'd be in the same situation of either having it in the ground when people don't want it anymore, or having a lot of demand and nothing left. And neither of those are a solution to the problem. Then there's higher interest rate. I won't go through all these in a lot of detail. Higher interest rate makes the price rise more steeply according to hoteling, which means that you'll have more stuff left in the ground. People don't want it as much, right? The price goes up more quickly. You can kind of see that there. We get to a price of 8 in period 6 now, between period 6 and 7, because the price is rising more steeply. So in order now to not have stuff left in the ground when the price is rising more quickly, it has to actually, the starting price has to drop. So instead of having a price that goes up like that, now the starting price drops and then it rises more quickly so that we have nothing left in the ground at the point when we want it. So you can ask questions about how interest rate policy affects resource use, right? It's going to have a big impact working its way through the spreadsheet. There's a smaller interest rate. It's the same one as before. Okay, and then we get into backstops, and this maybe will be the last thing that we talk about. I can talk about the monopoly thing really quickly on Monday next week. So the idea of a backstop is it messes with the spreadsheet a little bit. That's why I want to kind of point this out. Because with a backstop, here what I'm going to say is that there's a technology out there that we can consume as much as we want of at 6, a price of 6, okay? So now what we want to have happen is we want to get to no more oil left in the ground right when the price hits 6, okay? But the demand curve would sort of say that there's a constant positive level of consumption until we get up to 8. If you just sort of looked at the demand curve straight away, because the demand curve doesn't hit the intercept until we get to a price of 8. But now we're stopping before we get to the intercept. We're saying that there's a new backstop, the price at which we don't want it anymore is lower at 6. So now what we have to do is play around with the lambda until we get the price to be such it hits 6 right at the time when what I'm saying here is I guess we go from 37 to 42. Somewhere in here we hit 40. We run out, and it's just at the time between 5.6 and 5.99567 when we don't want it anymore because the solar technology is now there. Okay? So 2.481 seems to be the price that the lambda, the shadow price that gives us the starting price that does that. If we went down to 2, the starting price would drop, and in period 6, or I guess now we don't get to our backstop price until now down here around periods 8 or 9. That's 5.89, 6.28. But by the time we've gotten there, we've run out long before that. We're at 67 total units of extraction. So here we ran out sometime back here around periods 4 and 5, but the price is still well below solar, right? So we don't have a good backstop, but we don't have any oil either. This is what would happen when we wake up in the morning and we have no way to get to work, okay? But the Hotelling's rule says that's not going to happen because there's guys out there who own the oil who are going to say, if I hold on to this, it's going to be really valuable next period. No one's going to have any oil. I want to be the only one with a barrel. So I'm going to take less out today. When they take less out, we're going to end up basically with the lambda, the price today, going up, the starting price. So the alternative to that, you could go way up too high, and then you've got oil left in the ground, but the market forces people then taking the oil out faster, right? Because you've got some left in the future, so they say, I'll just take more out today and sell it, because if I wait, it's going to be worthless. I'm going to be up to a price of 6. Well, actually, I'm at a price of 6 today, immediately, so I might as well take it out, so that's going to push the supply up today and push lambda back down, okay? So we end up there with 2.481 as being the one that basically gets us to the solution, all right? So then the example here has a couple other backstops. I'll stop today because we're up to 11:20. But on Monday, what I'll talk about really, really quickly is how a monopolist differs from a competitive firm, okay? Now the thing is, the monopolist knows they're the only producer of oil. They own it all. They know that if they expand their production today, they're going to push down the price today, which is going to hurt their revenues, right? Same thing with a monopolist making cars. They restrict their supply of cars because they know if they sell too many, they push down the demand curve and they lower the price. The monopolist here is going to do the same thing, and what we're going to see is that's going to lead them to drag out the extraction, and they're going to run out later. They're going to produce less every period to extract some monopoly profits. And here they're actually running out in period 13 instead of 9. I'll explain why with some math. But this is the one place where they say the monopolist is the environmentalist's best friend. Because if you're a climate change activist, stretching out the exhaustion of all the carbon in the ground, like from 9 periods to 13 periods, whatever that means in real life, can really save us on climate change because it's all about taking it out later as opposed to earlier. Taking it out today means it does more damage for a longer period, okay? So monopolists can actually be good from a natural resource point of view. Okay, we've already seen how they can be bad in other contexts in terms of regulation and that sort of thing. Okay, so I think you know enough now to do the problems